taught this morning to my Cal 1 class. So remember, notation is very important for limits. If you have the limit of f of x as x approaches a equals L, remember the a is the x value you're approaching, and L is the answer, which your answer is the y value that it's going to. Okay, now always try direct substitution first, unless you can like see right away there's a problem. But so many people miss the easy ones because they're trying to work something out, and then you don't have to work it out. It's just if you plug it in and take the limit, that's the answer. Okay, so try that first all the time. So if you have the limit as x approaches 2 of 3x minus 5 over 5x minus 3, try plugging 2 in directly. So we've got 3 times 2 minus 5 over 5 times 2 minus 3. This is not going to be a problem, so it's just going to give us our limit. So our limit as x approaches 2 of that function is 1/7. Let's try the limit of t squared minus 9 over t minus 3 as x or as t approaches 3. Now here, if you try direct substitution, you're going to have a problem, right? Because that's going to give us 0 over 0. So in that case, we're going to go one step further and try to cancel something out so that we can do direct substitution. So always try factor whatever you can factor. T squared minus 9 is going to factor into what? Remember, if you, good, that's your difference of 2 squares. If you don't have that middle linear value, you can always, and it's a difference, you can factor it into the difference of 2 squares. So now we've got t minus 3 on top and bottom. That'll cancel. That's your removable discontinuity. That gets rid of your problem spot. So now we just need to take the limit as t approaches 3 of just t plus 3. And I know Professor's object drilled this into you. Notation, notation, notation. I know it's a pain, but keep writing the limit until you actually take the limit. So now when I'm ready to substitute it in, I'm taking the limit. I'm plugging 3 in for t. Okay, so that's kind of the basics. Try direct substitution. That doesn't work. Try factor in whatever you can, cancel it out. Here's another example. And this is when you've got something with a radical. So again, I would still try direct substitution, but that's going to give me a problem because I've got that, I would have 0 in the bottom. So this, whenever you see a radical, multiply top and bottom by its conjugate. So I'm going to multiply top and bottom by 4 plus x plus 2. So whatever you do to the top, you got to do to the bottom. Do y'all remember this kind of? Now, it kind of looks horrible algebraically, but it pans out neatly. So when you FOIL that top, I'm going to have the square root of 4x, 4 plus x times itself, which will get rid of the radical. And then when you do outside, I'm going to go ahead and write it out, but this will always happen when you multiply by the conjugate. If you do outside, I've got plus 2 times the square root of 4 plus x. Inside would be minus 2 times 4 plus x. And then last, I'm going to have a negative 4. So those middle terms will cancel each other out. And I've gotten rid of all the radicals on the top. And then on the bottom, just leave it alone. It looks messy, but don't try to distribute or simplify. Just leave it alone for the time being. And then let's simplify a little more. So our 4s will cancel. And that'll just leave us with x over x times that conjugate. Now, what will happen now? You can cancel the x's out because now that's a product in the bottom. And that eliminates our problem spot. Now that got rid of the problem spot, so now we can directly substitute. And we'll have 1 over square root of 4 plus 0 plus 2. So we end up with 1/4. That might be one of those ones that it's not easy to remember that, but if you know the little trick, it works out nicely. Okay, here is another limit situation. If I give you 1 over x minus 1 over 5 all over x minus 5. The little trick here is to multiply by the common denominator, which would be 5x. So if I multiply this by 5x, that will get rid of my fractions on top. But if I do it on the top, do it on the bottom also. Okay, so if I multiply 1 over x times 5x, what's that leave me with? Just 5. And then the same thing here. If I have 1 over 5 times 5x, what's that leave me with? X. And then we just have 5x times the denominator. Now it's something we can handle. I guess, though, I did the big mistake. What'd I forget? My limit notation. You'll better call me on that. Okay, so before I just try straight substitution, which if I did that, I'm still gonna have a problem at 5 because it would make this 0, right? Okay, so let's try to simplify it a little more. And notice you got 5 minus x looks real similar to x minus 5, but you're going to have to flip it around and pull out a negative for it to cancel out. So if you think of this as negative x plus 5, pull that negative out. And then you've got the x minus 5 that will cancel with the x minus 5 in the denominator, which was our problem. So now we have the limit as x approaches 5 of negative 1 over just 5x. And we can take the limit now and just have 5 times 5 on the bottom. Nice, huh? Okay, this next example is going to involve a sum of cubes or a difference of cubes. The example I'm going to give you is the sum of cubes, but I'll refresh you on the difference of cubes also. So here we're going to have the limit as x squared or x squared minus 4 over x cubed plus 8 as x approaches negative 2. So trying direct substitution, that gives us a negative 8 on the bottom plus 8. So that's a problem. So that tells us we got to simplify some. Just a little refresher. The sum of cubes so if you have a cubed plus b cubed is a plus b times a squared minus ab plus b squared. So all positives except for that AB is a negative when you do the sum of cubes. And then if you run into the difference of cubes, so if you had A cubed minus B cubed, that's going to be A minus B, and then all pluses in the quadratic part. A squared plus AB plus B squared. So if we're looking at our example, what will the top factor into? And then the bottom will be the x plus 2 x squared minus 2x plus 4, where your b is 2, the cube root of 8. So here our x plus 2's will cancel. And now when we do direct substitution, we don't have that problem spot. So negative 4 over 12, which will be negative 1/3. Okay, so that's the limit review. We will, at the end of this review, we do some limits of infinity and L'Hopital, but that's the beginning of calculus limit review. So if you can do all that, the test will be easy. Okay. So if you were watching this recording, this would be one video. And then the next part is going to be derivatives. And the links are in the notes too that have all the formulas, just to refresh your memory. The notation might be a little different from book to book, but it's generally the same. They might use different variables like H or C or whatever, but it's the same stuff. Okay. So don't get bogged down in what book uses what notation. Okay. We all love this. Remember this good old long way, the limit process. You probably block this out of your memory. This is the long way to find the derivative. Okay. F prime of X equals the limit as H goes to 0 of F of X plus H minus F of X over H. There will be one of these on the exam, and it'll probably be a quadratic. Okay. And it'll be, show me find the derivative by the limit process. That'll be the directions of it. So I know, you could probably tell me what this derivative is. Okay. But the reason you can do that is because somebody did the limit process to find it. Okay. So especially mathematics background, chemistry, not so much. You're going to be like, oh, there's computers that do all this for me. But mathematics, you need to know the process behind everything. So when I say find the derivative by the limit process, you're going to use that limit notation. So we're going to do the limit as H approaches 0. And I'm going to put a bracket here for this part. That's my first bracketed part. What does that mean to do? What does F of X plus H mean? What's F of 2 mean? If I say find F of 2, what am I telling you to do? Plug in 2, right? In for every X. Well, it's the same thing, but I'm telling you to plug in X plus H for every X. So everywhere I see an X, I'm replacing it with X plus H. So that's what F of X plus H means. So I'm going to have X plus H squared plus just X plus H plus 1. So that's my original function, and I plugged in X plus H everywhere there's a X. Okay, so that's that first chunk of the limit process. And now I need to do minus F of X, which is just rewrite the equation, the original equation. So if you want to, well, let me do it below it. This is my f of x plus h, and this is just my f of x. And then that's all over h. That's the hard part about this, is setting it up. Because everybody sees that f of x plus h and like, I don't know what to do there. So just relate it back to what you know how to do. Now just start simplifying. We're going to expand the squared, or FOIL it out. So that'll give us x squared plus 2xh plus h squared. And then I've just got the plus x plus h. I can drop the parentheses, plus 1. And then for this part, just make sure you change all the signs. So minus x squared minus x minus 1. And that's all over h. Okay, now what should happen here, and it should happen every time, is everything that doesn't have an h with it should cancel out. If it doesn't, there's something wrong with the math up top, like you didn't do a sign right or something. So here I've got an x squared and a negative x squared, got an x and a negative x, and I have a 1 and a negative 1. So I've got 2xh plus h squared plus h left on top, all over h. So if everything didn't have an h on the top, I couldn't pull an h out. And that's what's letting me actually take the limit, because that lets me cancel the h on the bottom. So I pulled an h out of every term on top. Now I can cancel that with the denominator. And I've got the limit, so h goes to 0, of just 2x plus h plus 1. So I've got 2x plus 0 plus 1, or 2x plus 1. So I'm going to ask you to do one of those. And then after that, you can use all the derivative shortcut rules. Which, and like I said, I'm going to go over them in like short term, but if you need more of them, they're all on those handouts. Okay, so the derivative rules. That you already have in your toolbox are, if I give you a function that's a constant, what's the derivative of any number? And then f of x equals x, what's the derivative of x? Okay, so that means that if I give you a constant times x, what's that derivative? It's just whatever the constant is. So like 3x, the derivative of 3x is just 3. Okay, and then we've got the power rule. And this really is appropriately named because the power rule does so much, especially when you get into integration. So if I have x to a power, and I'm doing this generically, like any n, what do you do? Pull it in the front, okay? So pull n out in front, and that's times x to the, what's the new power? N minus 1. Okay, and then if same thing, but say we had a constant in front, remember that constant just hangs out. So it's still the same process. You're just going to have the constant times n times x to the n minus 1. Okay, product rule. I think I actually say this differently than professor's object, but it's the same thing no matter which order you do it. So say I've got h of x equals the product of two functions, f of x times g of x. What's the derivative of that product? How do y'all say it? Y'all remember? Always do. The first times the derivative of the second plus the second times the derivative of the first. If I'm not sure, she might do the derivative of the first times the second plus the, but it doesn't matter because it's all addition and multiplication. So as long as you do the derivative of one times the other regular one plus the switch it, you're going to get the same answer. So the order might not be the same as mine, but it's the same equation. Now the quotient rule, on the other hand, the order does matter. So if I've got a quotient f of x divided by g of x, the derivative of that will be, you got to start with the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that one order does matter because it's subtraction. So you gotta make sure you start with the derivative of the bottom. I mean, with the bottom and times the derivative of the top. I said that completely wrong. Do as I wrote, not as I said. And then the last, like, real important rule is the chain rule. And my notation looks a little different here, but same thing. d over dx means take the derivative of f of x to a power. This is just one example. You know, the chain rule, you can have multiple different types. Kind of work from the outside in, but everything gets the derivative taken, but you can only do it once at a time. So we're going to start with the power, apply its rule. So bring the power down, and that's still going to be times f of x without doing anything to it. I've just applied the power rule. And then that's multiplied by the derivative of whatever is inside, or whatever is the inner function. So just I'm running out of room here, but just for example, say I had x squared plus 4x to the 5th. What would the derivative of that be? 5 times that whole thing to the, well, don't forget your power, to the 4th, and then times 2x plus 4. And that, I was running out of room, so that is not at all good notation, but you get the gist of it. Don't tell them professor's option. Okay, now here's a couple like special cases of taking the derivative. And so there's a video of all those rules, and then I have a special cases video. The first example, or our first special case, is the one where you have to factor out the least exponent. So let's say we have f of x equals x times the square root of x squared minus 1. Usually anytime you're taking the derivative or integrating, change any radicals to exponent. So let's go ahead and change that to x times x squared minus 1 to the 1/2. Because that's going to give you your option to use the power rule, which we know how to use. Okay, we turn that into something we can work with. So looking at this, let's take that derivative. Now you've got multiple things going on here. You've got to use, we've got a product, we've got x times x squared minus 1 to the 1/2. So we've got to use the product rule. And then on this, you also have to use the chain rule. Okay. So kind of like scope it out before you start. And so, and in your mind think, okay, I've got a product, and then this part is composition where I'm going to have to use the chain rule. Okay. So let's do a product. We got the first times the derivative of the second, and because this one's a little messy, I'm going to bracket it, or you put parentheses, but that is kind of my like sign that, okay, this is a separate entity that I'm working with. So just like that last example, I'm going to pull the power down, rewrite what's in the parentheses. What's my new power here? Negative 1/2. And then times 2x, the derivative of what's inside. So that's my derivative of the x squared minus 1 to the 1/2. Okay, so that's the first times the derivative of the second plus the second times the derivative of the first, which is just 1 here. Okay, so let's, sorry, I forgot my prime on my derivative. Clean up a little bit. Notice that you have a 1/2 here and a 2 here, and that's all multiplication. So you can cancel those. Now, if that had been plus 2x or minus 2x, don't do that. But if it's all multiplied together, you're good to go. So I've got x times x. So x squared times x squared minus 1 to the negative 1/2 plus x squared minus 1 to the 1/2. Now notice I've got x squared minus 1 twice. They're just raised to different powers. And that's where the factor out the least exponent comes in. Okay. So if you have like the parentheses are the same, but you have different powers, factor that out, pull out the least exponent from the whole thing. So I've got a negative 1/2 and a 1/2. So I'm going to pull out the negative 1/2. So I'm going to pull out, let me leave a little space here. X squared minus 1 to the negative 1/2. So I'm factoring that out of that whole thing. Okay. And again, I'm going to put my brackets here. So if I'm factoring something out, that means you're dividing out by it, right? So I've got to divide this term by x squared minus 1 to the negative 1/2 and this term. Okay, so on the first one, it's the same thing. So those just cancel, which just leaves me with that x squared. Now, when I do this one, what are you doing to exponents when you're dividing? Subtract them, right? So this means I have 1/2 minus a negative 1/2, which will give me 1/2 plus 1/2, which is what? 1/2 plus 1/2. What's a half plus a half? One whole. Okay, so that's my exponents. So that's just going to leave me with x squared minus 1 to the first power, which is just x squared minus 1. And now since that binomial in front is multiplied by that whole thing, I can move it down because it's a negative exponent under the whole thing, because now it's multiplied there. Okay. So now I've got x squared minus 1 to the 1/2, or you can put the radical back on it now, it doesn't matter. And then I've got x squared plus x squared minus 1 on the top, which leaves me with 2x squared minus 1. And that is your simplified answer. So when you see these, it'll say something with no fractions in the numerator and no negative exponents. Okay. Now, one thing on your homework in lumens on Canvas, a lot of times, did y'all notice last year, sometimes it'll take some really ugly answers and still count them right? Because technically they're correct. And that computer is just like checking equivalency, depending on how the question is coded. Okay, so if you sometimes on that homework, if you put this in there, it'll give you a green check mark. But when you get to the test, I'll give you partial credit for getting that far, but I'm not going to give you full credit until you get this far. So just be careful. Sometimes that homework will check stuff right, even if it's not simplified, just because it's saying, oh, that is equal, but it's not completely simplified. And it's just from whoever coded it to accept different answer types or not. Okay, so just be aware of that. A lot of times it'll do a fraction over a fraction, which drives me nuts. It'll have a big green check mark, and I'll be like, don't ever leave. That's like a grammatical error in math, so don't do that. Okay, how much time we got? Okay, I'm going to do 2 more examples that'll finish out these special cases. And then for Thursday's assignment, and I'll assign it to everybody, I'll do the other 2 videos for the first and second derivative test and integration. And that'll be your assignment for attending on Thursday. Okay, so let's finish. I've got, you might could finish on that page, but I'm writing too big. An implicit differentiation example. Okay, so say we've got x squared plus 9y squared minus 4x plus 3y minus 7 equals 0. And you're told to take the derivative with that with respect to x. Okay, so that's what the d over dx means. Means I'm taking the derivative with respect to x. The problem here is I've got a bunch of y's, right? Okay, so implicit, any other variable that you're not taking it with respect to gets its own d whatever dx. So since this is y, it gets its own dy dx. If we had a bunch of t's in theirs, it would get a dt dx, just whatever variable. This means I'm doing x normally. Anything else, anytime I see a y, I do the derivative of that, but then it gets times dy dx. Okay. So the first part of this, x squared, is just 2x, right? I'm gonna not put an equals there because there's some equals in the equation. But the next part, I've got the y variable. So I'm still going to take the derivative of it, which would be 18y, but then that's going to be times dy dx. And you can put y prime there if you want. Remember, y, if you do y prime equals dy dx, you can do that, but a lot of times that starts to look like y to the first power. So it's a little more tedious to write dy dx, but it might keep you from messing some stuff up. And then we've got minus, what's the derivative of 4x? Four. And then plus the derivative of 3y is 3, but since it's y, it gets a dy dx. And then the derivative of 7 is just 0. And the derivative of 0 is just 0. So we've taken the derivative of everything with respect to x. And then what you're gonna do is we're gonna solve for dy dx. So isolate, get all the dy dx's on one side and everything else on the other side. So I'm gonna leave the 18y dy dx and the 3 dy dx on that side, and everything else I'm moving over to the other side. I don't have to worry about the 0 because it's 0. So that's going to be negative 2x plus 4. Now think about that dy dx as a variable. I'm going to factor it out because they both have dy dx's. And then get that dy dx by itself. So dy dx equals negative 2x plus 4 over 18y plus 3. Just be careful with your signs there. The only other thing before I move on is be careful. Sometimes they want to stick in a product rule in there. If there was like a 4xy in the problem, that you've got to do the product on that because that's x times y. That's your product. Don't just do 1 times dy dx. Make sure you do the, and I'm pretty sure there's a homework problem with that in there. So just be aware of that. Okay, and then the last example we're going to do is find the equation of the tangent line. And remind me to shut the door next time. Okay, so say I've got y equals 2x squared plus 3x minus 4. And I want to find the equation of the tangent line at the point 210. And without graphing this, I know that's a parabola, right? Somewhere. And it's a u somewhere. Say 210 is right here. My tangent line is just going to touch at that point. So I'm looking for that equation. So I have a point. What else do you need to write an equation? Remember, equation of line, y equals mx plus b. I need a slope, which remember, the slope is the derivative. So you might have been thinking, what does this have to do with what we're doing? But that's the whole, the derivative is the slope, okay? So I'm going to find the derivative of that, which is 4x plus 3, right? So I could take and find the slope at any point along that parabola, but I want it at that specific point. So my slope for this line is going to be 4 times 2 plus 3. So I'm plugging this in to my slope formula. So I've got a slope of 11 right there. So now I've got a slope and a point, and you can do a couple different methods. I usually always go back to the point slope form. You could always use y equals mx plus b and find b. But just mathematically, mathematicians use the point slope form a lot more than finding b. So plug in, you got x1, y1 from the point they gave us. And we found the slope of 11. At 10. So we end up with y equals 11x minus 12. So that is a slope of the tangent line at that point. I mean, the equation of the tangent line, not just the slope. Okay, we covered half of Cal 1 today.